special. Remember, stopping time says that the event...
Stopping time is also at a random time.
There are lots of random times that are not stopping times. Oh, it's very fragile. Oh my God. Oh, please, everybody. Stopping time is very, very special. Remember it said, oh boy, let's over here. That's too big a distraction, but during office hours we'll talk about that. Yeah, that's, boy. Remember the definitions are very, very restrictive. So anyway, so it's a random time independent of everything. And mainly you just need this. So you can say that the expectation of this product is a product expectation that is beta to the k, done. All right, it's cute. So then it remains to, oh yeah, we have lots of time. It remains to go and solve this. Yeah, but, and remember the ACOE was like this too. We replace C with C tilde. The average cost problem, the relative value function was exactly a minimum like this, without this last term, and with S just a singleton, and C replaced by C tilde. So anyway, we talked about that earlier. Yeah, I won't get into that now. All right, any questions before I go on? Have you seen this before? No? Okay. Yeah. And by the way, you could call this by itself a Markov chain. I guess that would work too. That would be really ugly, as you could do that. The sequence beta to the k is a Markov chain, right? Beta k plus 1 equals beta times beta k. That's a Markov chain already. So that would work. That would work as well. It would just, again, it would be evolving on a. We would never find it state space. It would be ugly as hell.
So the main point here being that just saying like discounted cost problem or any of the other ones can be cast as a.
Yeah, it's really helpful just to say this is all I have to understand. Yeah, that's all. And I'm not cheating you, because the thing is that like this problem probably comes up in applications more than anything else. It's sort of like autonomous cars or something, or all sorts of energy applications. So all sorts of things are these finite horizon problems. And I've been just pushing. Why have I been pushing average cost? Everybody? Anybody? I've sort of said it. Anybody remember why?
When we can't have equilibrium points.
Oh.
So we need, or there's ultimate boundedness.
Yeah.
Well, when you can't get
yeah.
I think it's because when you can't get an equilibrium point, and so you're off with some equilibrium points, so you have to look at an average cost.
That's true. But you could also look at discounted. Discounted would also solve that issue of not having equilibrium. You're right. All these problems, average cost, this total cost, and discounted cost, all can handle cases where you don't have an equilibrium. But I focused on average cost because there's such a tight solidarity with the sort of total cost problem. And so for people from the control background, it's just a completely comfortable segue, That's the main reason. This is a beautiful solidarity between what you learn in a control course, a deterministic control course, and average cost optimal control. That's really, it's more pedagogical than anything, okay? Okay. But this is the mother of all optimal control problems. And then it's trivial. Should I do it, or should we just go to office hours? And do we want me to derive the discounted cost optimal? Should I? Maybe I should, because there may be fear out there, so I can kill all this, right? I don't think you see that very often, but let's just call it that. All right, so we're minimizing this over all sequences, u from 0 to infinity. And like I said before, you just take out the first term. You condition on x equals x. And so we know the first term, and then you write out the rest. And then I've got the remainder. And then I've got, how do I write it down? Yeah. Okay. Okay, cool. And so then you want to, basically you've got a condition. You've got to bring in our transition matrix somewhere. So we're going to condition on, we're something from 1 to infinity, so we're conditioning on x1. Oh yeah. So I'm summing over all y, and maybe I should be. I know Fubini's theorem is true, but it might confuse you. I'm taking the thing inside here and playing with it. So I'm looking at the summing over all possible y's. Taking the conditional expectation given x1 equals y, and then taking the probability of y given the past. And there we have it. All right. All right, so now it's really much clearer, I hope, that you can do this at two-stage minimization. I can minimize overall u1 to infinity and then u0. And it's really convenient, Fubini's theorem, you can flip these sums around. Well, forget it. So we're getting closer. I just made one change here. I'm reminding you that that's the control transition matrix, right? And I said that, and that's u naught. And I'm saying that we can, for a given u naught, we can minimize this, and then we can minimize overall u naught. That's the same thing. It's the order of minimization. So first I'm minimizing from u1 to infinity with u naught fixed, gives me a function u naught, then I minimize over u naught. And then I can go Fubini away. Where did I put the sum? Or maybe not, maybe we're done. I mean, that's it, isn't it? because the other thing that's not done is a damned y. I'll just write it down. I just want to really say this loudly, that when I minimize over u1 to infinity, I get to see at time 1, see what x1 is, and choose my u1 accordingly. And so I can take the min inside the sum because of that. Because u1 might be a function of x1, right? Yeah, it's allowed to be. u2 could be a function of x1 as well. So that swapping is what's crucial, and that's my definition of 8 star. This whole thing is just 8 star of y. And I'm hitting that by p summing over y. That's what I mean by that product. So that's it. Yeah. So it's trivial, but not. Yep. Where? Did I miss something?
Last
Oh, no. I'm using my operator notation that I want you to know. It's just that this whole thing is 8 star of y, and I'm summing over y of px to y times 8 star of y. Yeah. So I'm, again, just to be clear, I'm hitting 8 star by pu and then I evaluated x. All right. So that's it. End of MDPs. All right. You happy? Yeah.
Is there a lot more to controls than MDPs, or is this?
Oh God, Jesus Christ! Can you imagine? I mean, in terms of what's left, so. Oh Jesus, we've barely touched. Can you imagine? We did all of MDPs in 2 lectures. Is that true? I mean, the last lecture we did, it was crazy. 2 hours, we did value iteration, policy iteration, and linear programs. I've never done that in 2 hours before. I don't think anyone has. And so I must have had an extra cappuccino that morning. I don't know, but I'm glad. It's nice to just get it done, because unless well, you tell me, okay? Maybe don't kill me in the evaluations. Maybe send me an anonymous letter or something if it was too much. But it's sort of like there's so many sweet things to do. We have to decide whether we're going to really go in deep or not. So in terms of what what else is there? There are all sorts of computational methods specialized to different situations. The biggest gap. Can you imagine how important partial information is? So in a lot of control problems, you've got decent sensors. You don't know the ground truth exactly, but it's good enough. You pretend your sensor measurements are real and just go with it, solve the problem, right? But just imagine the stock market, just. Just unbelievable, the issues of partial information. I mean, it's like, and I don't even know what on earth where you'd begin, because I know that a lot of, like, maybe 20 years ago, you'd see books on MDPs, and they would take the state to be like the prices. And I mean, excuse my language, even though I didn't say it. It's so much stuff. Like, what is Trump going to tweet tonight? You know, I mean, what is, you know, I mean, really, I mean, how will the coronavirus spread? Is Italy honest about what's going on Downing Street in the UK? You know, what kind of coup are they planning? You know, it's some, you know, so that's why the whole business is about information gathering. The reason Morgan Stanley is so successful is that they can get the information that you and I can't get, you know. And so more information you have, the better. So anyway, so you have, you pretend there's a state out there, but you only have partial information about it. Yeah.
I have a question going back to this. So I understand the math.
Oh yeah.
But I guess just, you know, we have PU, and so in a typical control problem, the input to me is, you know, it's usually clear, like, is what that would be. But in this case, you know, how do you go about? I mean, we've taken for granted we have a control transition matrix.
Yeah.
How do you actually go about doing that?
That's another question. So in terms of open things, I mean, we haven't really played around much about being given a problem and how do you cook up a Markov model. You know, the stock market's a great example. You know.
So I guess if you want to elaborate on that, what would be the control inputs?
I don't know a lot about finance, you know, but like, you know, there's questions about, you know, where do you invest your money and when do you pull it out, you know, and those are your actions. Your actions are of all of these products I can purchase. When do I buy it and when do I sell it, based on the observations I have, and then people have come up with stochastic models, you know, for the evolution of stocks and all that. So Black-Scholes, you know, they pretended there was some multiplicative Brownian motion. Scholes, is that it? Yeah, I think so. Something like that. Doesn't matter. I'm not a finance person. But then you assume a geometric Brownian motion. And they, you know, basically that was an assumption. If there was no arbitrage, if the world was perfect, nobody had special information, it would be valid. But they got all sorts of cool formulas for hedging and things like that, based on that assumption. But then again, there was a fixation on the things I'm looking at, those prices, is the full information set that I care about for decision making. And I can't imagine anything more naive, you know. And I think there are finance books where they actually teach this stuff. I mean, that's true. I mean, when you go to Princeton and take finance courses, you will spend the first year and a half learning about Black-Scholes and stuff for derivative pricing or whatever. And forgetting completely about Boris Johnson's crazy antics in the UK and what that could do to the stock market, or diseases or whatever, you know, all that information. And so you've got to be brave. So you just stick it all together. You know, you've got your phi t is prices, you know, your best predictions about crazy antics, forecasts of disease and insanity. You know, seriously, like, you know, is there going to be somebody to be executed tomorrow? I don't know. Yeah, what would you put in here? The weather, I guess. I don't know. I'm just, you know, I'm kidding. But you go through and you do your best bet, and then you would, you know, hopefully be able to fit a Markov model to data, you know, and then go through and do it. And this is a case where you need some sort of approximate methods, of course.
Yeah, I guess in this case, you know, you would, if you have control decisions that you assume that you can actuate. How do you know that that's going to force the transition that? So how do you?
Well, your model might suck. Your model might suck.
Okay.
Oh yeah. Yeah.
You'd have to have historical decision making too
Yes.
in order to fit the control transition.
Well, and that's why, as far as I know, reinforcement learning has failed completely, because by the time you learn a model, the whole world's changed. Yeah. And so you need something faster. You need something, But, so I don't know what the state of the art is out there. That's all proprietary. But I know that the mainstream people in finance laugh at RL because they came in saying they could solve everything, and it was so slow it was worthless. But that's so that's one example. Advertising is another one. And it's sort of like the stock market. I basically have a budget, and I want to dump in advertising here or there and how. And I get to observe partial information about the reaction of the population, again, it's similar. And that leads to things called bandit problems, simple bandit problems and multi-end bandits. Which is sort of like there's arms in a bandit. If I pull one of them, I'll make a lot of money, and the other ones I don't pull so much. The arm pulls are where I advertise. Some might be cheap, but have a great reward. I'd love that. And I get to just pull a few of them. So in terms of, I don't know. There's others as well. But in terms of the theory, one is you prove that every partially observed MDP is fully observed. So we'll do that next lecture. I know a lot of you won't be here. We'll be sure that we record it. I think people will be off at spring break. And that's a sweet fact, but you can imagine what goes wrong. You start off with a finite state space MDP, you end up with an MDP in Rn. You go from 5 states to an uncountable number of states. So there's an explosion in complexity, And then 2, what? No, it's a fact. I'll prove it. It's beautiful. It's this idea of a belief state. Yeah. Oh, that's right. Even here I'm cheating. Here I'm actually taking my state to be things I observe. So this would be like a hat. Right? This would be a hack you'd use if you want to create a fully observed model. You put in forecasts. That could be a stupid thing to do. How many people are sick in Palermo, Italy? How insane is Boris? I'm mentioning people outside of the U.S. But you know what I mean? How sick in Iran? How sick are people in Iran? What is going to be the impact in Iran? It's absolutely. So, and you can't just take your forecasts and stick them in. It doesn't work. It can work. People do it, but it often doesn't work. So there's a notion of belief state. But then what people in these kinds of problems, advertising, they look at multi-bandits, there are beautiful hacks.
About one, what Naren was saying, does this mean like we sense a certain number of things, or we have access, like an agent playing chess can see the whole board, so that's fully observable. But like if we're trying to learn about the economy, we only can see a few number of things. But we take what we see, and then we assume that's the full information.
Not at all. No, not at all. No. This is something huge. Again, you take your maybe finite state MDP, you construct this mega state called the belief state, and that evolves as a Markov chain.
Oh, so you take your finite observations and construct something bigger?
I will do it next time. It's not something I can say in words in 2 minutes. I'll need a half an hour. Okay, yeah. So that's next lecture, yeah.
One parallel I could think of, like quickly, was like hidden Markov models and stuff.
That's what this is. Yeah, that's this is a theorem for hidden Markov models.
Okay.
Yeah, yeah. So you need some assumptions, of course. I mean, yeah, but under very, 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 very super general assumptions, you can always convert things into a partially observed problem into a fully observed problem. It's a wonderful result. And so that's a worthless result because you made the problem so complex you can't do anything with it. But then you get heuristics, you know, and you basically get beautiful like pseudo belief states. You know, and for multi-arm bandits, it's sort of like the mean expected reward, some sort of distribution of your expected reward, but you just look at it in terms of mean and confidence bounds. That's it. You know, and you call that the belief state, even though it's not. And then you go through and you derive DP equations based on that fake assumption, and you prove it works. So there's beautiful books on this. I mean, just there's incredible literature on this problem, and it has incredible impact in advertising. So a lot of people have gotten very rich on this stuff. And so we'll do that right after spring break, the beautiful hacks. Okay. Yeah. Just, it's called, I mean, one of the beautiful hacks is called UCB. And here's the funny thing is that, you know what UCB stands for to most of you?
Upper confidence bound.
Well, shut up. But to most academics, they'd say UC Berkeley. And so people at Berkeley love to pretend that's what it means. It was invented by, you know, I mean, Lai is going to be here in a few weeks, by the way. The guy who did all this stuff, he's going to be giving a lecture in the Information Institute in mid-March. He's coming to visit us. So, I mean, he's the master. He and Robbins completely created this beautiful area for multi-arm bandits, and he'll be lecturing in mid-March. So I'll send you information about that. Yeah, but he's at Stanford, not Berkeley. and the work was done at Columbia, New York, not not Berkeley. All right, cool. So that's fun. So off to NEB.